can calculate the change of energy or the change of enthalpy of a reaction, knowing that if you have a bond, it's because two atoms are attracted to each other, so they come together. They're very stable. If you want to separate them, you have to put energy in to separate them. So that's an endothermic step. You're putting in heat to break the bond apart. The opposite happens when two things that are attracted to each other come together. They become more stable when they come together, so they give off heat to come together. So energy is required to break the bond, pull things apart, but energy is released when bonds are formed, when two things come together and are more stable. So this is an endothermic, positive change of enthalpy, and this is exothermic, it's a negative change of enthalpy. And here's the same diagram showing that we're putting in energy to break bonds. These guys are all separated. Energy's coming out as we form bonds. And overall, we got more energy out than we put in, so this is exothermic. Here we're putting in energy to break bonds. Energy's coming out as we form. Overall, we put in more energy, so that one's endothermic. So we have these tables that tell us the average bond enthalpies. Average bond enthalpies will tell you how much energy is required to break a mole of bonds in a gaseous compound. So, and it's average because it's looking at all the different places you're going to find CH bonds. For example, if you found it in methane or ethane, you're going to have slightly different values and they're all average to this. So what we do is we add up how many bonds are we breaking, how much energy is required to break each one, and then we find out how many bonds are we forming and how much energy is coming out to form each one. And we just add those up. So for this one, first thing I have to do is I have to know what my molecule is. So I have to draw my Lewis dot structure for nitrogen. Nitrogen has 5 valence electrons. So I'm going to have 10 valence electrons altogether. So there's 2, 4, 6, 8, 10. So there's a triple bond. And these 3 fluorines, I know fluorine has 7 valence electrons. So here's 2, 4, 6, 7. 2, 4, 6, 7. So the fluorines have a single bond, and there's 3 of them. I'm just going to write this for the other 2. And so I'm going to have to put in energy to break 1 triple and 3 singles. And I can see that I'm going to get out energy making 2 of these nitrogen trifluorides. So the nitrogen has the 5 valence electrons. There's 2, 3, 4, 5. 2, 3, 4, 5. And I know the fluorine has 7, so I'll go 2, 4, 6, 7. And we'll go all the way around. So I know the fluorines are going to be singly bonded. So I can see that I have 6, 1, 2, 3, 4, 5, 6 single and nitrogen fluorine bonds. So what I'm going to do, first I'll see how much energy do I put in. So I'm going to put in enough energy to break this nitrogen bond that I took off my table from the previous slide, 491 kilojoules per mole. And I'm adding to that 3 times the amount it takes to break 1 bond. I'm doing it 3 times. So I'm breaking apart 3 moles of these, 155 kilojoules per mole. Oops, kilojoules per mole. And then I have, these bonds are forming, so as they form and become more stable, energy is given off. So I'm giving off the energy of 6 of these. 6 times 272. The hardest part is probably knowing what's a positive change, what's a negative change. I have to put in energy to break these, so these are going to be positive. I release energy to form this, so this is going to be negative. And when I do these minus that, I end up with overall, it's a negative change of 676 kilojoules per mole. So if I do that reaction, if I react 1 mole of nitrogen with 3 moles of fluorine to produce 2 moles of nitrogen trifluoride, I'll give off 676 kilojoules per mole. And if we were to do it the other way, well, now I'm going to break these 6 bonds, and I'm going to make these. So this would be positive for this side. It would be negative for this side. So it would be the exact same value, 676, I already forgot it, kilojoules per mole. But now it's going to be a positive change. Now it's going to be endothermic because we just flipped the sign. So it was exothermic the other way, and now if we flip it, it becomes endothermic.